Welcome to the complete chapter of permutations and combinations. This chapter answers one question: how many ways can we arrange or select things? Permutations are about arrangement where order matters, think passwords or setting charts. Combinations are about selections where order doesn't matter, think choosing a team or picking a ball. Before we start, we need one tool, the factorial. The factorial of a non-negative integer n is the product of all positive integers less than or equal to n. For example, factorial 5 is equal to 1 into 2 into 3 into 4 into 5. Remember the crucial definition, factorial 0 is equal to 1. This entire chapter is built on this single rule, the fundamental principle of counting. If one event can happen in n ways, the next event in n ways, then the total number of outcomes is m cross n, m into n. This rule is used in every permutations and combinations problem. For example, if a password has two letters and each letter can be from A to Z, then the first letter has 26 possibilities and the second also has 26. So total number of ways is equal to 26 into 26. Next example. How many three-digit numbers can you form from four digits if numbers should not repeat it? Since repetition is not allowed, you have four choices for the first digit, three choices for the second digit, and two choices for the third digit. Because once you choose a number, you can't select in next time. So total ways is equal to 4 into 3 into 2, that is 24 ways. Permutation is the number of ways to arrange R objects from a set of n distinct objects. Here the order is important. If the order changes, then permutation changes. For example, ABC is different from BAC because the order of letters changed. Similarly, 1 to 3 is not the same as 3 to 1. So arrangement is equal to permutation. Whenever order matters, like pin numbers, passwords, seating arrangements, or race rankings, we use permutations because changing orders changes the outcome. Permutation formula. If we have n objects and we want to arrange r of them, then the number of permutation is npr is equal to factorial n divided by factorial n minus r because r positions are being filled one by one. Special case. When we arrange all n objects in all n positions, the total number of arrangements is simply factorial n. For example, arranging 5 students in a line gives factorial 5 ways. Permutation example. How many ways to arrange three letters from A, B, C, D and E? This is 5p3, that is factorial 5 divided by factorial 5 minus 3, that is 2, is equal to 60. Permutation with repetition. If some objects repeat, like letters in a word, we divide by the factorial of their repetition. The formula becomes factorial n divided by factorial p, factorial q, factorial r, where p, q, r represent how many times each object is repeating. Example. In the word mathematics, there are 11 letters. Here, M, A and T repeats twice. So total distinct arrangements are factorial 11 by factorial 2 into 2 into 2. Similarly, in the word balloon, there are 7 letters. L repeats twice and O repeats twice. So total distinct arrangements are factorial 7 divided by factorial 2 into factorial 2. In the word balloon, the two L's look identical. So if we swap L1 and L2, the word still looks the same. But factorial n counts those two swaps as different. So we are overcounting. To fix this, we divide by the number of ways the repeated letters can internally rearrange themselves. This removes all duplicate arrangements. Next is circular permutation. When we arrange people in a straight line, every new position creates a new arrangement. So the total ways is factorial n. But in a circle, something special happens. If we rotate the whole circle, the arrangement looks exactly the same. Example, if four friends sitting around a round table, if everyone shifts one seat to the left or right, it still looks the same circle because everyone's relative positions stay the same. So circular arrangements have extra duplicates created by random. To remove these duplicates, we fix one person in one seat. Once one person is fixed, the circle becomes like a straight line for the remaining n minus 1 people. That can be arranged in factorial n minus 1 ways. That is why circular permutation is equal to factorial n minus 1. Now, restricted permutations. In permutations, when we apply special conditions, the arrangement changes. These are called Restricted permutations. Case 1. Together condition. When two or more objects must stay together is the condition, we treat them as a single block. So if k objects must stay together out of n, first treat the k objects as one super object. So instead of arranging on n people, we arrange n minus k people n plus one super object. So total object will be n minus k plus 1. And inside the block, k objects can permute among themselves. That is factorial k. So final permutation is equal to factorial n minus k plus 1 into factorial k. For example, arrange A, B, C, D such that A and B are always together. In this arrangement, we treat AB as one super object. So there are now three objects, that is AB, C and D. Arrangement inside AB is equal to factorial 2. So total ways is equal to factorial 3 into factorial 2, that is 12. Case 2. Not together. When two or more objects must not stay together is the condition, then we simply get the permutation by subtracting factorial n minus together condition, because not together is complement of together condition. Example, arrange A, B, C and D such that A and B must not sit together. Here total arrangement is factorial 4 where no conditions applied. Then together permutation is 12. We just solved earlier. So not together permutation will be 24 minus 12, that is 12 ways. Case 3. Fixed position conditions. Sometimes the question says A must always at the first position or digit cannot be 0 at the start. A must be at third positions, etc. This is called fixed position condition. Logic behind arrangement in these conditions is we lock or fix that position first, then arrange the remaining. For example, A, B, C, D arrangement says that first letter must be A. So we lock A at first letter, then arrange remaining three letters. Case 4. Avoiding certain positions. This is complementary of case 3. For example, arrange A, B, C, D is in such a way that A must not sit on seat 1. Solution. So total ways with no conditions is 4 objects, that is factorial 4, and permutation of fixed position we previously did is factorial 3. So permutation of A must not sit on seat 1 is total minus A must sit on seat 1. That is factorial 4 minus factorial 3, that is equal to 18. Combinations. Combination means selecting objects. Here the order does not matter. ABC and BAC are the same selection because the items selected are the same. So whenever order does not matter, we use combinations. For example, when we choose people for a team or pick books from a shelf, the order does not matter. Now combination formula. If we have n objects and we want to select r of them, the number of combinations is NCR. The formula is n divided by factorial r times factorial n minus r. We divide by factorial r because the r selected objects can internally arrange in factorial r ways, but all those arrangements represent the same selection. Example. Let's choose two objects from the four letters A, B, C, D. Here n is equal to 4 and r is equal to 2. So number of ways we can select them is 4C2, that is equal to factorial 4 divided by factorial 2 into factorial 2 is equal to 6. This means there are 6 possible selections. Second, a committee of 5 is to be formed from 6 men and 4 women such that it has exactly 3 men and 2 women. Solution, we must select 3 men from 6, that is 63, and 2 women from 4, that is 4C2. Since it's and we multiply the results. So 6C3 into 4C2 is equal to 120 ways. This is the most important difference in the whole chapter. Permutation means arrangement where order matters. Combination means selection where order does not matter. Once students learn this difference, half the chapter becomes easy. Example, suppose we choose two students from A, B, C. Selections with will be AB, AC or BC. But permutation will be ABBA, ACCA and CBBC. So total 6. There is a very powerful relation between permutation and combination. First select R objects, that is NCR ways, then arrange those R objects, that is factorial R ways. So total NCR into factorial R which equals NPR. This relation is frequently used in solving problems. Next, repeated selection allowed. When repetition is allowed, each position can be filled by any of the n choices again and again. So total number of ways becomes n to the power r. This is commonly used in password or pin number problems. Now, symmetry property and Pascal's identity. Choosing r items is the same as rejecting n minus r items is symmetry property. Pascal's identity helps in recursive combinations and binomial expansion. It is the backbone of Pascal's triangle. Here are two challenging questions that require you to synthesize permutation and combination and the fundamental counting principle. Pause the video and try to solve these questions fast. Solution 1. At least 4 bowlers means the team can have exactly 4, 5 or 6 bowlers. Since there are only 6 bowlers available, the remaining players must be non-bowlers. Here total 9 non-bowlers are available. So case 1 will be 4 bowlers and 7 non-bowlers. So combination will be 6C4 into 9C7. Similarly for case 2 it is 6C5 into 9C6, and case 3 it is 6C6 into 9C5. Now, the total number of ways is the sum of all cases. So, total ways is equal to 1170. Second solution. A 4-digit number must start with a digit 4 or greater than 4. So, first digit has 3 choices, 4, 5 or 6. So, 3 ways. Now, we have 5 digits left because repetition is not allowed to fill the remaining 3 places. The arrangement of the remaining 5 digits into 3 spots is 5p3 because here order matters. 4132 and 4231 can't be same. So total ways is equal to 3 into 5p3, that is 180. So you have now completed a detailed dive into permutation and combination. If you aced this tough problems, you are ready for anything this chapter throws at you. Don't forget to like, share and subscribe to my page for more detailed breakdowns and crystal clear explanations of every math topic. See you in the next lecture.